of the force velocity with respect to time, and this is of course proper time, which is independent of coordinate system. And look at this quantity. This quantity is the Christopher symbol, and this is the force velocity. These are the components of the force velocity. Now, if you look at this equation, there is something wrong in this equation. Can you spot it? Anybody can see something wrong? Yeah, exactly. Look here. Lambda cancel with lambda. Nu cancel with u. I am left with the nu, and so this one should be okay. Maybe there are more of this in the lecture. I didn't check it. Now, this equation is very important. In fact, this equation is the general activity equation. On the left-hand side, I have this what we call the Einstein tensor. This Einstein tensor describes how space-time are changing. And to the right-hand side, I have the energy momentum tensor. This is very important quantity in general relativity. It shows how energy flows from one point to another point in space-time. So in fact, this quantity represents matter, this quantity represents geometry. So there is a relation between geometry and matter in general relativity. Of course, we will go through this and see what is this? What is this Einstein tensor? We will see it later. Now here, this is a very famous experiment. This is called the principle of equivalence. Now, in principle of equivalence of this simple experiment, I have this lift moving with acceleration g upward. This is a lift which is on the ground. The principle of equivalence says that this guy here cannot distinguish of being in a lift moving with acceleration g, or if he is standing still on a place with acceleration g. So in fact, this is a correspondence between gravity and acceleration. Gravity and acceleration. Acceleration is equal to gravity. However, there is one important problem with this. What is the difference between here and there? You can see I just put point A, B, C, and this is the ground. This is the ground. So you can see that this point here has certain potential energy. Here it has more potential energy. Here we have different potential energy. So in fact, these points, as I move from down to up, I have tidal forces. Tidal forces caused by G here is different than here, different than here, different than there. It is very small, of course, in this case. The change in G is very small between this point, and that point, but there's a change in G. Here, G for all points is the same. So in fact, the difference between these two is the existence of tidal forces in this case. And this tidal forces in general relativity will be taken care of by Christopher symbols, as we are going to see. This is another experiment. This is a lift moving with G. And here I have an opening, and a light is coming through this hole and falls down on the other side. Meanwhile, of course, the light will take certain time to move from this point to the other side. While the light is moving from here to there, of course, the lift is moving with acceleration g. So in fact, the light will not hit this point, it will hit some point there. Of course, this difference here depends on g. This is very simple experiment that shows light is bending, but the bend of light here is caused by this acceleration of the lift or velocity or whatever. Now, Christoffel symbols. We defined yesterday Christoffel symbols in mathematics, and we said that Christoffel symbols are the change or rate of change of the metric with respect to coordinate systems. Now here another definition of the Christoffel symbol, and this definition, it is in terms of the basic what we call basic vectors. Now what are these basic vectors? Now you know in a rectangular coordinate system, the basic vectors are I, J, K. You know this. Now in general coordinate system, I don't have right angle between I, J, and K. I have an arbitrary angle. So in fact, I have to use a basis that fits the curvature of space-time. So in fact, these basic vectors I call here E lambda and EU. In fact, these basic vectors are influenced by the space-time or changes in space-time and the space-time manifold. And here I have a dot product. A dot product, we see how much these two vectors are aligned. How much these two vectors are aligned. So in fact, the Christoffel symbol is a measure of how the basic vectors are aligned. This is another definition or conceptual definition of the Christoffel symbol. Now, yesterday, we have seen, if I have a tensor, then if I take the derivative of the tensor, the derivative of the tensor is not a tensor. We have seen that derivative of tensor is not a tensor. So we just make simple mathematical arrangement, and we derive the quantity which follows the transformation law of a tensor. This is quantity which follows the transformation law of a tensor. I call it covariant derivative. So covariant derivative, the covariant derivative is not only the partial derivative of a quantity. I add to this a quantity such that this quantity, this whole quantity, is not changing or it changes according to the laws of tensors. So this quantity changes according to the laws of tensor. This is what we call covariant derivative. You will see more about it in coming lecture. Now, Riemann tensor, I will tell you a story here. We are in the morning and we like stories. There was a guy in primary school. This guy is called Gauss. And Gauss is very active, talking with this guy, hitting this guy, etc. So the professor or the teacher said, "Oh, how I can stop this guy from moving and etc." He told him, "Count for me 1 + 2 + 3 + 4 + 5 + 6 + 7 + 8 up to 100. So that when he's counting, the lecture will be finished, and he is not doing. He said, it is 5,125. He give it. How he did it? Easy. He add 1 plus 99, 2 plus 98, 3, etc. Okay, so you have up to 49 plus 51. You are left with two numbers, which is 50 and 100. This is Gauss. Gauss later became great mathematician, and he has students. One of the most distinguished students of Gauss is Riemann. So in fact, Riemann is a student of Gauss. What Riemann did? He did a new branch in mathematics called Riemannian geometry. Riemannian geometry, it is abstract ideas. Nobody knows about it. But this Riemannian geometry has something very important. I will let you know what is important about this Riemannian geometry. Einstein, when he established his special theory of relativity, as you know, special theory of relativity is in flat space-time. You don't have any gravitational forces. Now, to introduce gravitation in special relativity, he has to go to something deeper. He was looking in a mathematical structure that allows him to really write down something related to gravity. Now, what is this important thing that he thinks? What is the basic idea of having a mathematics which corresponds to reality? In reality, you have the physics law are the same in all coordinate systems. So in fact, if I want to establish an equation, a real equation that describes reality, now this equation should take care of this fact that physics law are the same in all coordinate systems. And the question is, what type of mathematics I need to implement this idea? The answer was tensor calculus. Tensor calculus is embedded here in Riemannian geometry. So in fact, Einstein was looking for this fact, and somebody told him, oh, there is tensor calculus. Once he knows about tensor calculus, he studied it in no time. He developed general relativity. So in fact, maybe you ask, why tensor? Why tensor in general relativity? So the answer is, tensor are quantities that are the same in all coordinate systems. Okay, when you move from one coordinate system to another, you have the tensors are always the same. Now, in this Riemann tensor, you can see you have 4 indices and you have two parts. One part here is the subtraction between two derivatives. Of course, this is a derivative of the Christopher symbol of the second kind. Okay, and of course, this consists of a metric. So derivative of a metric, that means second derivative of a metric. So each of these contain a second derivative of the metric. And this side here, I have the product of Christopher symbols. So I have the difference between the derivative of Christopher symbols, and here I have the product of Christopher symbols. We will see more. This is an equation. What that means? in reality. I will explain in a coming part. Now, the other important quantity in general relativity is what we call the Ricci tensor. The Ricci tensor, as you can see, this is a contraction of the Riemann tensor. I contract Riemann tensor by multiplying by G or something, and I will get the Ricci tensor. This is very important tensor in general relativity. Of course, again, you can see that the Ricci tensor is the difference between differentials of the Christopher symbol and the product of the Christopher symbols. Also, what is the meaning of the Ricci tensor? I will say this in a minute. I have another quantity in general relativity. I call it Ricci scalar. A Ricci scalar, look at this carefully. In fact, I multiply the Ricci tensor by the metric GUV. So if I make the multiplication here, you can see this cancel, rho, cancel, rho, etc. So in fact, I have here, I will have a pure number. This is a pure number. That is what we call the scalar. If you look at the end, this is all cancelled. So I have a pure number, and this is in fact a scalar quantity. Now I come back to the Einstein tensor. This is the Einstein tensor. So what Einstein tensor consists of? It consists of the Ricci tensor and the Ricci scalar. The Ricci tensor and the Ricci scalar. So in fact, this is the relation. This is what we call the Einstein tensor. Now let us see what is the Riemann tensor. If I take flat space-time and I take a vector on a flat space-time and I move the vector around the closed loop on a flat space-time, what I discover, this is here, I move it on a closed loop, I come back to the same point. When I come back to the same point, the vector coincides with itself. That means there is no change. Okay, if I have a vector moving in a flat space-time on a flat table like this, and I take it from one point and go back to the same point, so it will keep the same direction. It will not change. This is not true for curved space-time. For curved space-time, if I make parallel transportation of a vector, it will not return to its original, it will not exhibit the same direction as its original direction. So in fact, there is a change in direction when I move a vector in a curved space-time. So in fact, as you can see, if I have more curvature, I will have bigger difference. Small curvature, little difference. No curvature, this will return back the same. So in fact, the amount of the deviation of the vector from its original status depends on the curvature of space-time. Therefore, you see, so this quantity here, which is the Riemann tensor, is an expression of how much this vector will change when I move it on a curved space-time. The more curved space-time, I will have more deviation. Okay, so in fact, this Riemann tensor physically is an expression of how much space-time is changing, how much it is changing from one point to another point. Now look at this here. I have a curvilinear coordinate system. This is not rectangular, this is arbitrary curvilinear coordinate system. And this curvilinear coordinate system, I have, for example, this line here, because of curvature, it will deviate and become here. Please imagine that this is not a two-dimensional, it is a three-dimensional. Okay, so this is a volume here. This quantity here is a volume. It is not flat. It is a volume. So in fact, how I define the Ricci scalar and the Ricci tensor. The Ricci scalar is defined as how much volume is changing from I move one point to another point. Of course, if I move from here to here, I have this change of volume. If I move more further, I will have more change in volume. Here I have, in this part, I will have big change in volume. So in fact, how much change in volume I have, this is what the physical meaning of the Ricci tensor. But that is not all. Ricci tensor will not show you how much volume is changing, but in what direction as well. So in fact here, I have two quantities important, the volume and the direction. So the Ricci tensor is a quantity which shows you if you move and curve the space-time, how much volume is changing from when I move from one point to that point, and in what direction. The Ricci scalar, no. It is exactly the same. So I'll show you how much volume is changing when I move from one point to the other point, but it will not indicate anything about direction. It is a scalar quantity. So this is the difference between, or the physical interpretation of Ricci tensor and Ricci scalar. I come to a quantity which is very important in general. Unfortunately, yes?
I don't get what it means for a volume to change in a certain direction. Like what's the
Okay. See, I'm now moving in this direction. Okay, this could be another curve here. Okay, so I can move from one point here to another volume. I don't know how I present it here, but I present here just two curved space-time. I can have as many curved space-time as I have. Okay, so in each curve of space-time, I have different change. Okay, here I'm present just two. In fact, this is infinite. This is infinite. Yes.
واحنا ممكن نشبهها بان هو كأن في شعاعين مثلا ضوء ماشيين سوا وبعدين جم في منطقه فيها
لا ده فوليوم الشعاع.
لا انا اقصد ان الخطوط دي كانها ضوء برل بعدين لما جم في منطقه فيها كيرفيتشر المسافه ما بينهم او الفوليوم اللي ما بينهم اتغيرت.
طيب
هو ده المقصود.
ايوه. طيب I will go back to this moment of this. This is very important. Yes. And in general relativity, the most difficult thing to calculate is this energy momentum tensor. Energy momentum tensor contain many components as you have to see. And if you have the presence of electromagnetic field, the things will be much more complicated. One can ask me, what is the difference between this energy momentum tensor and what we use to talk with when when talking about Newtonian gravity. The Newtonian gravity, we don't have such a tensor. We have only one component of this tensor. This component is the energy density. As we are going to see, if I write Poisson's equation in Newtonian mechanics, I would have the right-hand term depends upon rho, what we call it, rho, which is the density of matter. In fact, this tensor, the energy momentum tensor, contains many things. And I come back to the idea of tensor. Somebody would ask me, what is the difference between a tensor and a vector? The answer is this. In a vector, you have components indicating directions. In a tensor, you don't have such a thing only. You have all what is related to that quantity. If I take the momentum tensor, I have the velocity, I have the density, I have the momentum, I have the energy, I have everything incorporated in one element. So one element, one tensor, contains so many information, or all the information about matter in this case. This is the continuity equation. Okay, so in fact, if I have the flow, this is the energy momentum tensor. In fact, this is just simple explanation. I have flow of energy and momentum, and of course, because of the equation of continuity, what is coming in is what is coming out. But this definition is very simple. Let us go to more about it, to understand more about the energy momentum tensor. The energy momentum tensor have components like this: 2, 0, 0, 0, 1, etc. So this part here, u equal to 0, energy, okay, and this is spatial dimension 1, 2, 3, and this is the time dimension, which is the 0. This is the momentum. So these components are the momentum, etc. As I said, whenever I have problem with generative, the most important thing is how to write down the momentum tensor. And that depends upon the particular situation. If I want to apply this one in free space, what I get? 0. Because this one, the energy momentum tensor, describes matter. In empty space, I don't have matter, and the tensor is 0. If I go to the universe, no. In the universe as a whole, there's matter. So the energy momentum tensor is not 0. It is something complicated, as we are going to see. If I'm talking about wormholes, for example, the energy momentum tensor is quite different. In a black hole, also the energy momentum tensor is quite different. So in fact, this energy momentum tensor depends upon the particular problem I am having or I am addressing. Again, I'm just insisting on this energy momentum tensor. This is the energy momentum tensor, and you can see this is time. I'm writing the momentum density, momentum flowing through time. Okay, how momentum is flowing through time, and here how it is flowing through space, etc. So in fact, each of these has a certain meaning in the energy momentum tensor, and each of these has to be evaluated. Each one for a particular problem, we have to evaluate what is t, tx, etc. That depends upon the particular situation we are discussing. Now I will go to another concept in general relativity, which is the geodesy. I think all of you heard about geodesy. Geodesy. What is a geodesy? Shortest distance between 2 points. If I have flat space-time, what is the shortest distance? Straight line. If I have the surface of a sphere, what is the geodesy? Great circle. Exactly. So in fact, the geodesy depends upon the curvature of space-time. Geodesy depends upon the curvature of space-time. This is the basic idea of geodesy. Now this is a mathematical representation of this. If I have a forward velocity and acceleration is given by this quantity, in geodesy I will have 0. That means if I am moving on the geodesy line, I have no acceleration. If I am following a geodesy line, I have no acceleration. Acceleration happens, of course, with respect to not external observer, according to myself. I will not talk more about this. This is in fact the equation of geodesy, general equation of geodesy and general relativity. Okay, again, is there any second question? Let us see. No, I think this is right. Okay, this time this is right. Okay, so in fact, this is the derivative of forward velocity. This equation of general relativity. This is the acceleration of space-time. This term here is the components of the forward velocity, and this is the Christoffel symbol corresponding to the curvature of space-time. Whenever I have a curvature of space-time, I have this Christoffel symbol present. Yeah. Now let us compare general relativity or the geodesic and general relativity to Newtonian mechanics. Now you can see here m multiplied by the derivative with respect to proper time, which is the acceleration. Here it is the same. Mass times acceleration. Mass. Here I have a potential. And here what I have this quantity. So in fact this quantity here is equivalent to the potential in Newtonian mechanics. This is the potential in Newtonian mechanics, and this quantity is equivalent to the potential in Newtonian mechanics. This quantity depends upon the curvature of space-time and the forward velocity. I think this is the last slide, and I am just trying to listen to your questions. Yes, please.
يعني الجزء ده هنا اللي هو بيعبر عن البوتنشال ده نقدر برضه نعتبره اللي هو في الحاله بتاعت النسبيه ده الكيرفيتشر بقى بتاع السبيس تايم.
له علاقه بالكيرفيتشر مش
الكيرفيتشر.
له علاقه. Yes. T0. اكتشف ان التي 0 هي النيوتونية equivalent تي 0 وكل
باين باين
شوف التصوير باين ولا مش باين؟
مش سامع ومش فاهم.
عايزه يشوف الدكتور ورا بيتكلم. الدكتور اللي باين يعني باين اهو.
in space time. This method is a flow from one point to another. Now, this flow could be moving of something, or it could be even change in electromagnetic field. So all this with certain velocity. Now, all this is expressed with these components I have written in the energy momentum. So the energy momentum principle doesn't give you just the density as in Newtonian mechanics. It gives you the density as well as all other features of energy and momentum. The difference between Newton and Einstein is that Newton neglects all energy and momentum in space-time. So we come up with the equation T mu equal to rho, which is the density of space only. And you will see this in Poisson's equation. Okay, so in fact, I will talk in the last lecture, or I will discuss the last lecture. I don't want to set it now. What is the difference between the solution I'm going to find and what others found data? على فكرة, what we are going to see in general relativity. General relativity was introduced by Einstein. Einstein introduced just the equation. Who solved it? The first guy who solved it is Schwarzschild. Later, as you said, De Sitter. And before De Sitter, there's Friedman. Friedman is the most important solution. I'm going to discuss it with you or to talk about in the last lecture.
The first
Others couldn't. So in fact, this equation of general relativity contains many things and it has many solutions. Each solution depends on the particular case. If I want to talk about wormholes, I have to find energy momentum tensor that corresponds to these wormholes. And I have to find a solution consistent with general relativity. So in fact, general relativity has many solutions. Here in this workshop, we'll talk about only one solution, which is the simplest. We call it Schwarzschild solution in a free space, where I have the energy momentum tensor is equal to 0. Okay? If it is not 0, we will talk about what happens if it is not 0. Yes?
Solution depends only on the coordinates.
On?
Depends only on the coordinate system.
No, it depends upon the structure of matter. The solution depends upon the energy momentum tensor. Is it 0? Free space. It is not 0, then what particular case I have? So the solution, I think if you go deep, if you want to specialize in general relativity, I hope that you yourself, you can find a solution to the field equation. So the solution of field equation is open. There are many solutions. Each solution depends on the particular case. How I define the energy momentum tensor in curved space-time? Yes.
For the mass
times both sides of the equation. Does this relate to the gravitational mass equal to the inertial mass?
No, I'm not going to this.
Does it relate to this?
Not in right hand side, yes. On the right hand side, yes. In the left hand side, I think it should be the same, but you know the concepts are quite different. I cannot now talk about on the left hand side. I cannot talk about the gravitational and inertial mass. Any other question? Torsion. Second torsion. You have to. Torsion. That means you have to define your energy momentum characteristics. You have torsion. You have to define your. You have to write down the proper energy momentum and sort it accordingly. The solution in the presence of energy momentum tensor is much more complicated than the free space, but the idea is the same. As I said, in general relativity, these field equations are very elegant, and you can adjust it to solve particular problem. How to make it solve that problem? You choose the right energy momentum tensor. Not only this, there's another factor you can introduce in the field equation or in the solution of the field equation that characterize the system you are having. We will see this in the last lecture. Okay, shukran. Thank you.